Hi everyone, thank you so much for joining the video. Here are today's learning objectives. The first is to know the colours of the oxidation states of vanadium and its compounds, and to understand redox reactions for the interconvention of the oxidation states of vanadium in terms of the relevant standard electrode potential values. So now we're going to talk about the variable oxidation states in transition elements. So transition elements show variable oxidation states, and this is because of their part 4 d orbitals. The redox potential for a transition metal changing from a higher to a lower oxidation state is influenced by pH and also by the ligand. But in general, it is easier to oxidize a transition metal in alkaline conditions and reduce a transition metal in acidic conditions. So the example that you need to know is vanadium. So vanadium exists in oxidation states 4, 3, and 2, and they're all formed by the reduction of vanadate 5 ions by zinc in acidic solution. So we start off with this. Vanadate 5 ion, and so we have VO2 plus, and then it gets reduced by zinc, and so the oxidation state of the vanadium becomes +4, and then it gets reduced again, so it becomes +3, and then finally it becomes a V2 plus ion, which has an oxidation state of +2. You also need to remember the colours of these different vanadium species, and a way that you can remember that is if you remember the acronym, you better get vanadium. So if you remember that order, then you should be able to remember the colours. If you do forget the oxidation states, you can just work it out. So for example, if I take this +4, we have VO2 plus. So the oxygens we know are -2, and then because the overall charge is +2, that means we need x minus 2 equals +2, because the individual oxidation states need to add up to the overall charge. And so we get that the oxidation state of the vanadium is equal to +4. Now we're going to talk about why vanadate 5 ions are reduced by zinc. So these are all the standard electrode potentials of the vanadium species that we have. And so if I tell you that the standard electrode potential of zinc, well, the equation is Zn2 plus 2 electrons goes to form zinc, because for these standard electrode potentials, the convention is always to write them as reduction reactions. And if I tell you that its value is minus 0.76 volts, we can see why it reduces all of these vanadium species. And it's because this value is much more negative. So it's more negative than all of the vanadium species. And so electrons will always flow from this half cell to the other half cell, if you remember back to your electrode potentials, because this more easily loses the electrons. So we have that electrons are more easily lost, and so electrons travel from this zinc to the vanadium species. So if we were going to look at the reaction between zinc and this vanadate 5 ion, if we write out the equations, we should be able to see what's going on. So the electrons are being lost from this zinc half cell, and so this means that the reaction must be going to the left because it's giving away electrons. And so we've got a zinc, and then also this added with 2 of these vanadate 5 ions and 4 H pluses and 2 electrons to form Zn2 plus 2 electrons plus 2 VO2 plus ions and 2 waters. So now we can cancel out the electrons. And so this is the overall equation that we get. So the zinc is being oxidized to form Zn2 plus here. This is oxidation of zinc. And this vanadate is being reduced to form this VO2 plus ion. And so the general thing is that because the standard electrode potential of this zinc Zn2 plus half cell is a lot more negative than all of these standard electrode potentials for the vanadium species, that means that it will reduce all of these vanadium species until we finally get to V2 plus.